Okay, hello. Um, Good afternoon. Sorry for the delay. I was facing some technical difficulties. I hope they go away. My laptop seemed to be struggling a little bit. Okay, so we are talking about synchronization. So we let's go through the slides. We looked at the ATM example. We looked at the problem with race condition. We examined the too much milk problem. We looked at a bunch of different solutions. Okay, so the last thing that we mentioned in the last lecture was the solution that we came up with, the last solution, which only used atomic load and stores, kind of solves the problem that we had with too much milk problem. Ensures that only one thread gets into the critical section, but as we discussed, it was very unsatisfactory. And we discussed 4 reasons for that. The last thing that I mentioned, but I didn't have time to go over, was that this solution only works if your system executes instructions in the same order that you have coded. And then I mentioned that most of the systems actually do not execute your code in the same order. And we kind of touch on the 2 main reasons that this doesn't happen. The first one being the compiler. So the compiler does some optimizations, and one of the optimizations that the compiler does is that it analyzes your code. If it finds that there are instructions that are not dependent, it feels free to reorder them. So that's the first one. Even if you disable optimizations in your compiler and you start running your code on most of modern architectures, the hardware might do this reordering. So at runtime, the hardware, your processor, might identify instructions that are not dependent, so they're working on different data, and hardware might decide to reorder those instructions to get performance. Now let's look at an example. So I have 2 threads here. Thread 1 sets P to some computation. So there is this function that does some computation, and the result goes to P. And once this is done, we set P initialized to true, so that this P initialized is supposed to become true once P is initialized. In thread 2, we have this while loop that will wait on P initialized, and as long as it's false, it waits there. The moment P initialized becomes true, it assumes that P is initialized, so it sets Q to be some function of P. And the next line after that, we say, if Q is not some function of P, then panic. Now, the question is, can this code panic? And the answer is, it depends, right? If this code executes in the same order that you have written it, then it won't panic, because P initialized becomes true only after P is indeed initialized. However, if at runtime or at compile time, the instructions are reordered, there is no guarantee that this code doesn't panic. In particular, in thread 1, we have two instructions, p equals some computation, and then p initialized equals true. So when the compiler is compiling this code, the compiler might find these two instructions independent because one of them is setting p and the other one is setting p initialized. These are two different addresses in memory and they're unrelated. So the compiler or the hardware might in fact reorder these. So it might well be that we first execute p initialize equals true, and then we go and set p to some computation. Now, if we get interrupted in the middle of this computation and context switch to thread 2, now in thread 2, p initialized is true. So this while loop does not wait. And we're going to go here. So with a garbage p, so a p that is garbage, whatever it was in p, it's not that some computation that we wanted. We're going to calculate q. And there's a probability and possibility that we get interrupted. We go back now to thread 1. Thread 1 now completes this p equals some computation. And then we context switch back to thread 2. Now p is set, so we do this sum function again, and we check q with that, and this is going to be triggered because they're not equal, and our code could panic. Here is another example, very similar to that one. So this is, you can assume that this data is that p, and this new is that some computation. So in CPU 1, I'm running data equals new, and then flag equals set. In CPU 2, these two lines are basically while flag not equal new. So as long as flag is not new, we're going to wait here. So we're going to just go between these two instructions again and again and again. And once flag is set to, sorry, not new, set. So when flag is set, then we're going to read data and put it in R2. Very similar to the previous example. And the intuition is R2 eventually will be data, but as I mentioned, this is not going to be true all the time because the compiler or the hardware might reorder these two instructions. Now, this is a good place to talk about sequential consistency and basically memory consistency as a whole. So memory consistency talks about the order of memory operations in a multiprocessor or in a multi-threaded system. I think in particular in multiprocessors, because that's where it gets really important. When you have a bunch of processors running on the same system, accessing the same memory. Sequential consistency says that the order of instructions for each thread is the same as what the programmer has coded. So there should be no reordering of any instruction within one thread. Now, when two threads are running at the same time, any interleaving is possible as long as the order of instructions per CPU or per thread is the same. So it remains the same. For example, as long as you do data equals new and flag equals set with this order, meaning that you first do the first one and then do the second one, so you have sequential consistency. The same with the other one. So as long as you're not reordering the instructions that are executing in program 2, then you have a sequential consistency. Your system provides sequential consistency, and it doesn't matter how they interleave. For example, if I move this S1 before L1, that's fine because I haven't changed the order in CPU1. So the order between what CPU1 is accessing memory and what CPU2 is accessing memory, the order of those instructions does not matter. All that matters is that the order we basically adhere to the programming order for our programs. So basically, if we do this, then this is not consistent. This is not sequential consistency. So if I reorder these two instructions, this is not going to be sequential consistency. Now, sequential consistency is what probably you thought your system does. Basically, the code that you write is the code that executes. Unfortunately, that's not the case. The reason is, implementing sequential consistency and making sure that instructions execute in the same order that the programmer wants has a performance cost, and we want higher performance. So most systems, including x86, have a different memory consistency model. In particular, in x86, you are allowed to reorder loads and stores in the same program. So here is an example. So the code I have on CPU1 has S1. So this is a store. We're storing new in X. Then there is a read or a load. So we are loading X to R1. And then we load Y to R2. Now, in x86 memory consistency, we are allowed to reorder this store after the loads. So it's allowed to happen that way. The way it works actually is by putting load buffers. So if you have taken any computer architecture course, if you're taking it or you will come across this word, this phrase of store buffer. So what happens is in CPU1, when you execute x equals new, so you're writing new to address of the variable x, this store does not directly go to memory. It will go to a buffer on CPU1. And it stays there. At some point, when the buffer gets full, the content of this buffer will be written in memory. And the reason we are putting this buffer is because of performance, because we know that if we go to memory, it's going to be expensive. So we say, okay, this write is going to eventually be written in memory. So I'm not going to be worried about it. Now, when this read happens, this read, instead of first going to memory, it first goes to that buffer and checks the content of that buffer. If it finds out that this X has been written to in that buffer, it reads the value from that buffer instead of going to memory. Now, what happens is this could happen. So I have two stores here. In CPU2, I'm now writing to Y, and then reading Y, and then reading X. So here again, this write could be reordered. So x86 allows this reordering to happen, and the result becomes something like this. So the reason I have this point here is because this read R1 equals X reads its content not from memory, but from the load buffer, from the store buffer. So it actually reads new, but in CPU2, when I'm reading X, this buffer doesn't exist. So I'm going to go to memory. So in CPU1, I have X equals new in my buffer, But in CPU2, there is nothing in the buffer, so I'm going to go to memory. Now, the result of this write has not yet been written to memory, so this guy reads 0. The same here, when CPU1 is reading Y, the content is in the store buffer in CPU2, and it hasn't yet gone to the memory. So we can read 0. So as you can see, if you look at this memory order, which is what at the end happens, we can see that these writes have been reordered in comparison to these reads. And this is something that you should be aware of. So this is basically x86 model. And if you're writing code for x86, which is basically probably most of your coding that you're going to be doing, you have to be careful that your instructions could be reordered. Okay, so going back, so this was an aside. This was kind of like an advanced topic, just to let you know. Now, moving forward, unless otherwise stated, we're going to assume that the programs that we're writing are going to execute the same order that we're writing them. But as I said, in reality, that's not necessarily the case. Okay, so let's move on to solution 4, because solution 3, although it was a solution, but it was not really satisfactory. So solution 4, we're going to introduce synchronization objects. So what if there was something like a lock I could use? So if I come to the refrigerator and I see there is no milk, I can put a lock on the refrigerator and say nobody has any permission to open the refrigerator because I want to go and buy milk. So I want to be the only one who is doing it. So this is kind of like, it might be annoying if your roommate wants to, let's say, drink orange juice, right? But let's say we have this. So we're going to introduce this object that we're going to call mutex. And we're going to say this mutex has two operations, a lock operation and an unlock operation. So when you lock a mutex, nobody else can lock it. And if they want to lock it, they're going to be suspended. So that's how it's going to work. You lock a mutex. If in future anybody else wants to lock the mutex, they're going to be suspended. They're going to go to waiting state. So the operating system is going to change their state to waiting. And later on, when you unlock, then others can come and lock the mutex. Okay, so that's the logic that we're going to put. So now, if we have this object, how can we use it to solve our problem? So it's going to be super easy now. The way I'm going to code this time, this is solution number 4. This is my critical section. If you remember, I want to check if there is milk, and if not, go and buy milk. So I just put a mutex lock and mutex unlock before and after my critical section. And by doing this, I am creating mutual exclusion, because if I am successfully locking the mutex, anybody else who attempts to do it is going to be blocked. And therefore, nobody else can run the code that comes after the lock until I unlock the mutex. At that point, others can go and lock the mutex. So we're going to say any code that we put between lock and unlock is our critical section. So I got a very good question. So somebody's asking, are compilers hardware instructed to not reorder mutex locks and unlocks? And the answer is yes. So mutex lock and unlock ensures that any instruction that comes before a lock cannot be reordered with any instruction that comes after the lock. So you have some code here, and then you have this mutex.lock, and then some other code here. So none of these codes here, none of these lines, none of these instructions can be reordered after this lock. So this won't be allowed. Now, these instructions can be reordered here. That's fine. But they cannot be reordered after the lock. The same with unlock. So when you have unlock, any instruction that comes here cannot be reordered before this unlock. This won't be allowed. They can be reordered after the unlock, but they cannot come before. And the instructions that you have inside, they can be reordered inside, but not before or after the lock. So basically, it's kind of like a memory barrier. It doesn't allow instructions to be reordered across these barriers. That was a really good question. Okay. Now, let's talk about rules of using mutex. One quick point. Here, I'm just telling you that this object exists and we can use it, and we'll use it. In the next part of the course, when we talk about multi-threaded kernels, we're going to talk about how we can implement it, because this is a service that the operating system is providing to programmers, to processes, mutex, semaphores, condition variables. So next lecture, in the next portion of the course, we'll talk about implementing them. But for now, I'm just introducing them to you, and we're going to just use them as tools for synchronization. I got another question. Since mutex has to be treated especially by the compiler, is it not possible to make a user-defined mutex? As far as I know, I can't think of system-provided mutex in C. You can actually. So the mutex doesn't necessarily need to be implemented by operating system. When we actually go and in the next portion of the course, when we start talking about implementing mutex, I will tell you ways that you can actually implement mutex in user space. So we'll talk about that. So good question, wait on that. For now, let's assume that it's provided by the operating system. For now, we'll talk about different implementations of mutex later. Okay, what are the rules in using mutexes? First of all, the best place to put mutex is at the beginning of your function. So this means that your functions should. So if you actually have a modular design, then this should be easy. If you have a really long function that touches so many different data, and some of them are shared, some of them are not, then it means that you have a bad function. You have to break this function into sub-functions, and then have one function that actually touches the shared data. And at the beginning of that function, put your mutex.lock. And the best place to put the unlock is at the end of your function. So before you return from your function, call mutex.unlock. Never lock a mutex and throw a pointer to the mutex to someone else to unlock. So this is bad design. It makes your code unreadable because somebody has to then trace who has the pointer to the mutex. Get the mutex, lock it in your function. At the end of it, unlock it. This is the best way of coding, and it makes your code understandable. If you are throwing these mutex pointers here and there, so somebody locks it and then somebody else unlocks it, it makes your read extremely hard to debug and extremely hard to understand. Never ever access shared data without locking a mutex. Never, even if it is tempting. Here is an example. Let's say there is this global pointer p. So let's say it's a p star p. It's global, and initially it's null. So initially I have a null pointer. Then I have a bunch of threads, and these threads are going to call get p. So I'm kind of explaining single tone design pattern, design architecture. So get p, when it's called to return p, it checks if p is null, then it initializes it with an object. So it creates an object and it sets it to p and then returns p. If p is not initialized, sorry, if p is initialized, then it returns p. It doesn't reinitialize it. So basically the intention is to just have one object for p. Now, every time you're going to call p, get p, you're going to check if p is null or not. And it's going to be null only once. So the first one who calls get p is going to get a null, and then that guy is going to initialize p. And from there on, everybody is going to see a p that is initialized. So you might be tempted to do double checking. And by double checking, I mean you, without locking a mutex, you first check p if it is null or not. So you say, if p is equal to null, this means that p is not initialized, so I have to go and initialize it. Now, at this point, you might actually lock the mutex and then go and initialize your p, and then unlock, and then return. Now, next time, now p is initialized, so next person who calls get p, they're going to check again if p is null, and it's not going to be null, so it's going to return p. So with this design, what happens is that this mutex is not going to be called again and again and again and again. It's going to be called once or twice, right? Depending on, let's say two threads at the same time called get p, then one of them is going to lock the mutex, the other one will attempt to lock, and then it gets blocked, and eventually p gets initialized, and from there on you will never ever call lock. Now, so this is very tempting, this design, because you're not going to pay the cost of calling mutex.lock that often. And as I said, if locking mutex means operating system involvement, it means that it's expensive. So we want to avoid it. And this might be tempting to you to use. Now, the question is, does this work? Would this cause race condition? And if you remember, race condition means sometimes it's gonna, the output depends on the timing. So sometimes you're gonna get good results, sometimes you're not gonna get good results. If you look at this, you might think, yeah, this looks great. But in reality, it's not going to work actually, because of the reordering that we talked about, the compiler reordering and the processor or hardware reordering. What's going to happen is between this mutex lock and unlock, you have a bunch of instructions that there are some relationship between them, but some of them are unrelated. For instance, these three are not related. All three of them depend on the first one. So you have to first set temp to this memory region. But after that, instruction number, so this happens, this should happen before everybody else. But then the compiler can reorder the last one to run the second one, because it doesn't depend on the other two. So this is possible. This is a valid reordering, if you wish, because p equals temp is unrelated to temp field equals something, right? Now let's assume that you run this guy first, you go and run this guy second, and then you get interrupted. And now we go to thread 2, who is going to call get p. Now thread 2 calls get p. At this point, p is indeed initialized because we actually set p to temp. So p is no longer null. So now this second thread is going to assume that p is initialized, and it's going to return p, and this guy is going to go and use p. But in reality, p is still garbage. We still haven't set the elements and fields of p. So this code, because of reordering, is not going to work. This is actually called, it has a name. It's called double checked locking because of this double checking here. So we're checking this p equals null twice, and it's not going to work. So the one that works is the one that you actually lock the mutex before you access your shared data. This is an access to shared data. This check to see if p is null or not is access to shared data. And as I said in the previous slide, you always have to lock your mutex before accessing shared data. Now this design will work and it's correct, but it's costly, right? Because now every time you call get p, you're going to attempt to call the mutex.lock, and that's expensive, but at least it's correct, right? So this mutex that only we need to lock it once will end up having to lock it every time we want to access p, which is unfortunate but necessary. Okay, I got 2 questions. So how would you define synchronization in terms of the rules we're discussing here? Is synchronization ensuring that a race condition doesn't happen? No. Synchronization does not mean that race condition doesn't happen. Synchronization means data race doesn't happen. So I really wanted to avoid this discussion, but it was kind of brought up even in the last lecture. And then I said, ask that question later. So there was this slide that I think it was here. So when I defined race condition, where was it? Here. So here, when I was defining race condition, I said race condition is basically a condition where the outcome of your concurrent program depends on the order and the timing of threads. And this often, this was the question 2 people asked. This often happens when threads share some data. So, and then people ask me, can this happen without sharing data? And I said, keep that question. Now, there is another term that is data race. So data race is a condition where two threads access shared data without mutual exclusion. So there is a possibility that two threads access shared data simultaneously. And that is called data race. And it's bad. Race condition, if you have data race, then you will most probably have race condition. If you have unsynchronized access to shared data, then with high probability, you're going to have race condition, meaning that if you run your programs, depending on the order that your threads will run, you're going to get different results, which we saw, right, in the example that we had like 3 different kinds of x equals 3, 13, blah, blah, blah. Now, there are examples that you don't have race condition. You don't have data race. Let's say you're using synchronization objects. So 2 threads are not touching the shared data simultaneously. Let's say you're using locks, but because you're using locks in a bad way or in an appropriate way, then you still have race condition. And if you're interested, I don't have time for going through an example. Just search internet for race condition versus data race, and you will see a bunch of examples. So there are multiple examples where you don't have data race. There is no data race, meaning that 2 threads are not simultaneously touching shared data, but still the output of your program depends on the order of the execution. So you still have race condition. So I'm going to actually leave it at that. Again, as I said, I unfortunately don't have time to go over those. Even this part, I wish you had seen it before, like talking about threads and synchronization. And then we would have just spent time talking about operating system providing synchronization. But unfortunately, you haven't. So we're doing it here in OS course, talking about synchronization. But anyhow, so that's another topic for you guys to, if you're interested, go and look at. Okay, so yes, so going back to the question, synchronization means avoiding data race, avoiding the condition where 2 threads touch shared data at the same time. So that's what synchronization objects are going to be doing for us. They're not going to necessarily prevent race condition. If they're used properly, then they will avoid race condition. If they're not used properly, you could still have race condition, but they will definitely prevent data race. Okay. Can you set mutex on memory rather than code? Can you set mutexes on memory rather than code? I don't understand that question. Can you maybe explain what you mean by that question? I don't understand it. Okay. Now let's continue. Let's look at an example. So this is going to be a reoccurring example throughout this lecture. So we're going to come back to this example again and again. As we learn more synchronization objects, we're going to just use them to re-implement this example. So here is an example. It's called producer-consumer problem. So basically, there is a producer, there is a buffer, and there are consumers, or there is one consumer, doesn't matter. There could be multiple producer, multiple consumer, one producer, one consumer, one producer, bunch of consumers, doesn't matter. But there is the producers maybe produce items and they put it in this buffer. And then the consumers consume from the buffer. So that's what we want. Now, we need synchronization objects because this buffer is shared data, because producers want to use it to put their items, and consumers want to use it to consume items. So it's a shared memory object that multiple threads are going to access, and we want it to be protected. We want to have mutual exclusion when it comes to this buffer. So in particular, we want producers to wait if this buffer is full. So if the buffer is full, we don't want producers to put another item because there is no space. That's where the bounded comes. It's a bounded. It has a max. Once it's full, we don't want to put more. We also want consumers to not read garbage if the buffer is empty. So if there is no item in the buffer, the consumers should not be able to read anything from the buffer. Examples of this are, for those of you who have pipelined processes in command prompt. For example, you do ls and then use a pipe and then grep something. So in this case, ls is the producer. It produces characters or text for grep to consume and search over to find foo, right? So this is one example of producer consumer. There are other examples in reality. For example, you have these vending machines, right? You put something in it, so somebody comes in, fills them, and then people grab them. Or this Pepsi or Coca-Cola machines, don't drink those. I hate both of them. Those machines, right? Somebody goes, fills them up, and then some people who don't care about their health go and buy and drink. Don't take it personally. Yeah, just don't drink Pepsi. Sorry if I said you don't care about your health. You might be, but you might not think it through. It's bad. I don't want to be canceled. But anyhow, okay, moving on. So let's see how we can implement this with mutex. So now we have this really cool synchronization object. Let's see how we can use it to implement these bounded buffers. So before going there, let's put all the requirements that we want to implement. So there are 3 of them. The first one is the consumers should wait if the buffer is empty. The second, what about root beer? Yeah. The second one is that the producer should wait if the buffer is full. And the third one is that only one thread at a time has to have access to the buffer to manipulate the buffer. So either putting an item or removing an item. So you want only one, let's say the buffer is half full. So there is a space and there are items. And now 2 threads come. One of them is a producer, one of them is a consumer. You want one of them to go and manipulate the state of the buffer. Either the consumer goes and consumes an item, or the producer goes and puts an item. If both of them can go, then you might get a buffer with a state that is not consistent, right? Because in the middle of one of them reading, the other one is writing, and then you have a mess. So you want to avoid that. Here is how you can write the producer function. So note here that I'm putting try to produce, not produce, but I will talk about this, why it's try to produce. So as I said, we're going to lock the mutex at the beginning and unlock it at the end. So that's the first thing I want you to note. I'm putting the mutexes at the beginning and the end of my function. Now, for this, I'm defining a success variable that is initialized to false. Then I check once I have the mutex locked, so I have, mutual exclusion. So I'm the only one who can manipulate the state of the buffer. So I check if the size of the buffer is less than max, then there is empty space for me to produce or to put the item. Then I get the buffer and then in queue the item that I have. So the item that I wanted to put in the buffer, I can put it. And then I set the success to true. And then I unlock and return success. So if the size is less than max, then this function, if it's able to put the item, returns success. Otherwise, it returns false. Okay. Now let's look at the consumer, the code for the consumer. So again, at the beginning of the consumer and the end of the consumer, I'm going to lock a mutex, the same mutex. So both of them are using the same mutex. I called it BB, bounded buffer mutex. So in the consumer, it's the story is vice versa. So the item is initialized to null, and then we check if there are items in the buffer. So if the size is not empty, then we dequeue and we return. And again, note that I have tried to consume. So if this is successful, meaning that if there are items on the queue, then it returns one of them. And if it's empty, then it returns null. Now, let's say try to consume returns null. So let's say I say if try to consume equals null, cout buffer is empty. My question to you, when this line is being executed, is the buffer definitely empty? And the answer is we don't know. When we had the lock inside, it was empty, and that's why it returned null. But now that we don't have the mutex locked, another thread might have come and put an item. So outside, when I don't hold the lock, when I don't have the mutex locked, I cannot say anything about the state of the buffer. Inside here, when I have the mutex locked, I can say something about the state of the buffer, because nobody else can manipulate it, because it's a critical section and I have mutual exclusion. So I'm the only one who has access to this buffer. So here I can say else buffer is empty, cout buffer is empty, right? Blah, blah. So this would be valid because inside I have the mutex locked, so I can say something about the state of the buffer. But here in this other case, because I don't have the lock, I can't say anything about the state of the buffer, because somebody else could come, lock the mutex and manipulate it. And because I don't have the lock, I don't have the mutex locked, I can't say anything about it. So I don't know. So the answer is no. So if it returns null, right after it returns, we can't say anything about the about the buffer, because somebody else could now go and manipulate it. So is it a good idea to have this while try to consume equals null, not equal null in our code? Let's say you actually want to consume the item. You're waiting for this to return. Can I do this? Can I just put this try to consume in a while loop, and just, you know, while on it, like just repeat it again and again and again until it returns something that is not null? This is not a good idea. The reason is, let's say if you have a single CPU, for example, you could end up just not allowing the producers to go and produce the item. Because if your code constantly locks, checks, there is nothing, and gets out, again locks, checks, unlocks, again locks, checks, unlocks, you're not going to allow the producers to lock and put an item and get out. So you're going to damage yourself. You're going to just keep waiting, and you're not going to allow the producers to produce. Now, would it be a good idea if I say, you know, instead of just having this while like this, I put this while and then a sleep here, sleep, like for some number of seconds, and then this is probably a little bit better, but it's still not a good way of doing it. So we have to have another synchronization object that solves this problem for us. And that's where semaphores and condition variables come in. So basically, the mutex can only, if I go back to these constraints that we wanted, so out of these three, two of them are scheduling constraints, meaning that this waiting, that, you know, the consumer should wait if the buffer is empty, and the producer should wait if the buffer is full. We can't really get this with mutex alone. That's why we have this try to consume and try to produce. Mutex only gives us this mutual exclusion. For these two, we need other synchronization objects. So that will be the next thing that we're going to see. Okay, so that's that. And that's a segue for us to now start talking about semaphores. Okay, so I got a question. So currently we are locking and unlocking code snippets to prevent other threads from running the snippet without the lock. Can we do the same thing with memory, i.e. lock, unlock a specific memory blocks? I still have a hard time understanding the question, but if I get it correctly, do you mean that you want to tell the hardware that this variable, like, yeah, it's hard for me. Yes, so the first portion of your question is right. We're using this lock and unlock for snippets of our code to ensure that only one thread can execute them. But this is not just a snippet of our code. For example, if I go back here, as you can see, this buffer is somewhere in memory, right? This buffer is stored in memory. By putting these locks and making sure that only one thread can get into these codes, I'm indirectly making sure that only one thread can read buffer, which lives in memory. So it's a memory block. So buffer resides in memory. And by using this lock and unlock, I'm going to make sure that only one thread can access these memory blocks. So although it's a snippet of my code, but it's related to something that resides in memory. Hopefully I answered your question. Okay, so semaphores. What are semaphores? So semaphores are kind of like generalized lock and more. So they do what mutexes do, but they also do more. Now, they were defined by Dijkstra in late 60s. And if you are wondering, this is Dijkstra font. You can download it. It's for free. It's based on Dijkstra's handwriting. So I really like the font. So, and it's free. You can get it. So apparently I answered that question. Good. Now, it's unfortunately the main synchronization primitive that was used in original Unix, and probably even currently used in Linux kernels. I'm not sure though about the current state if it is the primary object, but in the original Unix, semaphores were the main primitive for synchronization. Now, semaphores are like integers, but they're non-negative. So they're either 0 or more, and you get to initialize them. So you give them an initial value. You initialize them to a non-negative integer. And after that, after initialization, there are only two operations allowed on them. The first operation is P, and it's an atomic operation that waits for the semaphore to become positive, then decrements it. So atomically, this P is going to check the semaphore's value. So when you say semaphore.p, what's going to happen is atomically, you're going to check the value. If the value is not positive, you're going to wait. If it is positive, then you decrement it. So if it is 1 or 2, you decrement it, and you get out. So that's P. And when I say atomically, I mean all of it happens or none of it happens, right? Now, the second one, the V operation, increments the semaphore by 1. So whatever the value is, you increment it, you add +1 to it, and then if there are waiting threads, you wake them up. Okay. So in Dutch, P stands for whatever that is that I cannot pronounce, and it means test. So P is kind of like you test the value of semaphore, and V is to increment whatever that other one is. I have it there, but I don't know how to pronounce it. But it means increment. So P is to test and V is to increment. In some software packages, some system libraries, P is usually implemented as wait. So it waits, and V is a signal. So P, this waiting is in it, right? So you wait until the semaphore becomes positive. And then in V, you kind of signal another thread to go and do whatever they wanted to do if they're waiting. So they don't have any negative value. So that's first. So they're like integers, but they don't have any value, negative value. The only two operations that are allowed on semaphores are P and V. So you cannot check the value of a semaphore. You cannot, if you have a semaphore, let's say S, you cannot say if S equals 2, then do something, because you cannot see the value of S. It's not allowed. all you can do with S is to call P or V on it. That's all you can do. So you can initialize them. Let's say you can initialize your value with 0 or 1 or 2 or whatever. So the initialization is allowed, but after that you can only call P and V on it. So somebody is asking, is there some sort of ready queue of threads that call P? I feel like otherwise there could be race condition of multiple threads trying to use resources. So I'm not going to talk about the internals of semaphores, how we can implement semaphores. That comes next when we're done with synchronization and deadlocks. Then in the next lecture, we talk about how operating systems can provide semaphores. Of course, we need some help, and we need to make sure that there is no race condition, right? So implementing semaphores comes next. For now, let's just learn them and use them, okay? We will talk about how to implement them. Another question is, how does the OS make an operation atomic? We'll talk about it. Okay, so let's just assume that they exist for now. I know it's painful to hear what I'm saying, to wait, but please wait. So for now, let's just assume that they exist and they're atomic. And then we'll see how we can implement them. Soon. After this lecture is done, next lecture, we're going to talk about them. Okay. That's that. And these operations are atomic, meaning that if two threads call P, operating system or whoever is implementing semaphores will make sure that only one of them executes P at a time. So two threads cannot be executing P at the same time. So one of them executes P and then the other one executes P. So at this point, we should be sure that these are atomic. So who implements them atomically, we'll talk about it later. In particular, we say how operating systems implement semaphores. But if you have thread 1, T1 calls semaphore.p, and then T2 also calls semaphore.p. Operating system makes sure that, for example, maybe T2 runs first this operation and then T1, or T1 runs first and then T2. Both of them cannot execute P at the same time. So that is guaranteed. The same with P and V. So if two threads, one of them is calling P and the other one is calling V, one of them runs first and then the other one runs, right? Either we first run V and then P, or we first run V and then P. We can't run them at the same time. So they're atomic. Even if somebody calls them at the same time. So the operating system makes sure that they're going to be atomic. Okay. Yeah, so basically what this means is in P, so when you're executing P, you're doing a bunch of stuff, right? And one of them is to go to a sleep, which we will talk about. So one of the operations that was in P was a sleep. And when you're executing V, one of the operations is to wake up someone. So if you don't have these two atomic, then you might get interrupted in the middle of this, and then, sorry, before you go to sleep, for example, you get interrupted and then you go and run V, and then this is going to wake up, but then nobody is sleeping, and then you come back and go to sleep and you might miss this. But this never happens, right? This scenario that I just said, that you get interrupted here and then you go and execute this does not happen. So when you start P, you're going to finish P, and then somebody can then call V. You're not going to interleave between P and V. They're going to be atomic. So P happens and then V happens, or V happens and then P happens, right? We're not going to interleave between them. Let me clean this, please, for God's sake. So here's an animation that I spent so much time on designing it, although not now, but when I designed it, it took some time. So let's say I have this semaphore that I have initialized it to 2. So the initial value is 2. Okay, now you can go. How is this disappearing? Please disappear. Oh. Hard. Oh my God. Okay, it went away. Okay, so we have this semaphore initialized to 2. Now the first train comes, it's going to call P. Because the value was 2, the value will decrement to 1, and the train goes. Let's say another train comes, it decrements the value to 0 atomically, and everything now is going smoothly. Let's say another train comes. Now the value is 0, right? So this train is going to wait because the value is not positive, is not more than 0, so it's going to wait. Now, if one of these trains calls V, then the value increments and somebody is signaled, and then the value, it decrements. So once V is executed, we finish P, right? So P then goes and decrements. So V increments, P decrements, and so on and so forth. So as long as this value is not more than 0, if somebody calls P, they're going to just wait. Okay. Now let's use this new fancy object that we learned, basically semaphores, to implement this bounded buffer example that we had, that we initially implemented with mutex, and we had this difficulty that we had to have this try, consume and try to produce. Now let's use semaphores to implement them. Now the rule, so a general rule of thumb for using semaphores is to use one semaphore for each of these, for each constraint that you have, that you want to implement. In the bounded buffer, we have 3 constraints, so we're going to have 3 semaphores for each constraint. Now, the way we're going to use semaphores, how they work depends on how you initialize them. So in particular, the initial value of a semaphore, if you want to use it as a mutex, you should initialize it to 1, right? If you're, and this is called binary semaphores. So if your semaphore is initialized to 1, then you can just use semaphore.p as very similar to mutex.lock, and semaphore.v very similar to mutex.unlock. And you can see why, right? Because if it's initialized to 1, it means that here in P, only one thread can decrement it to 0 and enter the critical section. And the next threads that come, and they call P, because now it's 0, they're going to just wait. So this is a way for us to get mutual exclusion. Now, this is good for mutual exclusion. Now let's see how we can use it for scheduling constraints, meaning that if we want somebody to wait for certain event to happen, then we can initialize our semaphore to 0 if we want to use it for scheduling. We can initialize it to 0. Then whoever wants to wait for a particular event they can just call P. Because it's 0, they're going to wait, right? And then whoever wants to create this event kind of signal the ones who are waiting, they can just call V. So this way, we're just using semaphores for these signals between the threads. So the one who wants to wait calls P and gets suspended. And then the one who wants to say, OK, the event that you were waiting for has happened, calls V. Now, let's now look at the bounded buffer example. So we're going to have this empty slot. So for the producers to wait, we want producers to wait if the empty slot becomes 0, right? When there is no empty slot, then we want producers to start waiting. Now, initially, your buffer is empty, so you can initialize your empty slot semaphore to max. So for max number of P's, all of the threads are going to be able to just go and produce because you have maximum number of items empty in your buffer. But when it becomes 0, when your buffer is full, then empty slot becomes 0. Now the next producer who calls P is going to wait. For the consumers, initially your buffer is empty, so you want them to wait. If they want to consume something, you want them to wait. So we're going to initialize the full slots to 0 because initially we don't have any full slots. And for mutual exclusion, so basically anybody who wants to modify the state of the buffer has to, we want mutual exclusion. For that, so don't mistake this. This is name. Don't mistake it with the class mutex. So this is a semaphore, but because we are going to use this semaphore for mutual exclusion, I called it mutex. So again, and then going back to the previous slide, I mentioned that if you initialize your semaphore to 1, you can kind of use it as you can use it for mutual exclusion. Now let's look at how you can rewrite the producer. Now notice first thing here, I don't have the try anymore. So it's not a try to produce, it's a produce. So once it returns, it has already put the item in the queue. And if it has to wait, it will wait in the middle of this function. Now, the first thing that this guy is going to do is to do the scheduling mutex. So it's a producer. So it calls empty slot.p to make sure that there is empty slot. And if there was, now you want to go and modify the state of the queue. So now you want mutual exclusion. So you use the mutex. So here is I'm using the semaphore for mutual exclusion. So this is my critical section. And I'm protecting my critical section with this semaphore mutex thing. Now, once I'm done, I want to signal the consumers, if there are any, to tell them that there is an item. So now I use the full slots V to signal potential consumers that are waiting to go out and consume. Now there is an item. So I call full slot.v. So this is kind of if you go back to the slide, it's kind of like a signal that I'm sending to the consumers. Now, if you look at the consumer's code, it's kind of like vice versa. Again, I don't have try to consume. It's really consume. So these guys are going to wait on this full slot.p. So if there are items, then we want to allow them to go and read or consume them. So if full slot is non-zero, it's positive, strictly positive, then this goes through. And after that, again, I have my critical section that I want mutual exclusion. So I protect it with this mutex.p and mutex.v. And once I consume an item, I want to tell the producers that there is an empty space. So I have consumed it. Now there is an empty space. You can now put your item there, and then I return. So if you look at this, producers are sending signals to consumers, and consumers are sending signals to producers. And then both of them are using the mutex for mutual exclusion to wait. So are there cases when a semaphore can go over its initial value? Yes. Yes. Oh, no, actually, sorry. Let me see. In this, so in general, yes, but in this example, never, right? In this example, this never happens. In general, yes. So, you know, you can initialize your semaphore to 1 and then call a bunch of V's on it, and it just goes up. It increments your semaphore. But in this particular example, I mean, look at this. This semaphore full slot is 0. If you call produce 10 times, then full slot becomes 10. Now, can full stop become more than max? No, because the moment full stop becomes max, then empty slot has become 0. So another producer cannot produce anymore, right? So in this particular example, we're sure that these empty slots and full stops are always between 0 and max because of the way we're designing it. But in general, yes, I mean, as I said, this full slot, we initialized it to 0, but it could go all the way to max. But we kind of, because of our design, make sure that both of them, full slots and empty slots, will always be less than max. So that we are sure because of our design. Hopefully I did not confuse you and answered your question. So I repeat myself. Yes, the value could go above what you initialize it. And in this particular example, it actually happens. So we initialize full slot to 0, but then the full slot could become 1, 2, 3, 4, all the way to max. But because of our design, it cannot be more than max. The same with empty slots. Empty slots is going to be between 0 and max because of our design. Wait, but don't we call V on full slots? Yes, we do. So what? So yes, here we are calling V on full slot. So let's say initially I create 3 threads to call produce. So what will happen is full slots becomes 3, and then I might create 3 threads to call consume, and then they make full slot go back to 0. So it's possible. Okay, now okay, so so let's stop here. For just I love this this video, so just for a little bit of fun, let's watch this video so that next lecture, when I talk about this slide, you have an idea who this guy is. So let me click on this. Let's see if it works. And let's watch it together. Do I have? Sucks. Let's see. I totally want to do this. Yeah, somebody knows him. So let me share screen on my laptop and let's watch him. It's so legendary. I love this. Okay.
Order. The government chief whip has absolutely no business whatsoever shouting from a sedentary position. Order! The honourable gentleman will remain in the chamber. When...
Sorry? It still is. Yeah, I know what I'm doing.
Since when an amendment has...
Order. I know what I'm doing.
When he turns up at our children's school as a parent, he's a very well-behaved fellow. Be a good boy!
That at any time in our history.
I apologise for interrupting the Prime Minister. There is simply far too much noise. The public doesn't like it, and neither do I.
This government or that Labour Party led by Jeremy Corbyn.
We don't name people in the chamber. People must observe the rules. No, order! Order! Order, I am simply and politely informing the Prime Minister of the very long established procedure with which everybody, including the Prime Minister, must comply.
Mr. Lewis.
Get a grip of yourself, man. Calm. Take up yoga, you'll find it beneficial, man. I say to member, order. Resume your seat, Mr. Harper. You don't stand when I'm standing, and that's the end of it.
Mr. Angus Brendan McNeil.
Calm yourself. You may be a cheeky chappy, but you're also an exceptionally noisy one. The Prime Minister will please withdraw the word idiot. It's unparliamentary. A simple withdrawal will suffice. We're grateful. Order. Put it back. Hello.
Legendary. Yeah. So watch the video. Definitely. It's like 3 minutes. I already puts like almost 2 minutes of it. Order. So yeah. Anyhow, thank you for sticking around. We'll talk to you on Thursday. Oh no, today's Thursday. What day is it today? Today's Thursday. Talk to you on Tuesday. So sorry. Take care. Be safe. We'll see you on Tuesday. Bye bye.